Welcome to a new set of exciting lectures. Today we're going to make an introduction to parallel programming using threads, explicit threads, and also introduce some vocabulary and fundamental concepts so that we are all on the same playing field here. So we'll go through this particular lecture is about vocabulary and fundamental concepts. And this slide we show a graph of tasks, and we say that tasks operate on data. So the blue squares here are the tasks. They operate on some data, and the data are represented by the green boxes here. Data that comes from one task and which goes into another task is called dependencies. And they are, in this graph, mostly shown as data dependencies, but they could also be control dependencies. Important thing here is that once the task has the data it needs for its operations, it can execute. And you can see here that in this particular graph there is some parallelism, for instance, here, where three tasks have the data available at the same time and can then execute in parallel. These two tasks can execute in parallel, and depending on how long the execution time of P and Q are, P and Q could possibly be executing in parallel with S here also. But there is a critical path here, and this typically goes maybe from, it's the longest execution time here through tasks, and that is also an important concept here. So F needs A here, and G needs the data from F. And then, depending on if H or R is the longest, the critical path goes like this, typically. So this is called the critical path. There are various kinds of parallelism that we need to talk about. One of the most important one is data parallelism. So data parallelism is any kind of parallelism that grows with the data set. And this is a very good kind of parallelism because it means that you can scale up the performance by just simply adding more data to the algorithm to give it. So the more data you give to the algorithm, the more tasks you can have. So typically the tasks are somehow defined by dividing the data among the tasks. So if you have So one option is that if you give the algorithm more data, you can have more tasks with the same size. Or if you have another option is that you have the same number of tasks but with more data per task, which sort of increases the granularity of the task here. And this is another concept here that is important to consider, granularity. So larger grained tasks typically are good because then you can sort of offset the parallelism overhead with the amount of work in each task. But on the other hand, with large grained tasks, you have little options for load balancing here. The generation of the tasks in a data parallel program can be either flat, so the tasks are generated by sort of one thread or at once, or it could be recursive, meaning that a task can then in turn generate new tasks and to a certain sort of degree of granularity. Operations on the data in each task could be the same, but they can also be different. The important thing here is the data grows with the data set size. That is what defines data parallelism here. And again, I want to reinforce that data parallelism is the best kind of parallelism because this is a scalable kind of parallelism. The more data you bring to the algorithm, the more parallelism you have. The other kind of parallelism is functional parallelism or functional decomposition. In the functional decomposition, you assign tasks to distinct functions in the program. So here is a graph showing different tasks in some kind of weather prediction algorithm. So you have some kind of model for the atmosphere, you have an ocean model, hydrology model, and land surface model. And they interact in different ways. And you make a task for each of these models that can execute in parallel, and then they interact while executing. This is, in some cases, a very natural way of defining a parallel program. A drawback, perhaps, is that it can only scale to constant factor. If in this example, if these 4 tasks sort of have the same kind of execution time or execution behavior, then the speed up, or the amount of how much faster you can execute this code compared to a sequential version, can at the most be 4 times, because you have 4 tasks, and if they are of equal complexity, then you can possibly get 4 times faster execution compared to serial. But each functional task could be data parallel. And if you have working in a model where functional decomposition or functional parallelism can sort of coexist or be composed with data parallel models, then you can take advantage of both functional parallelism and data parallelism. But not all programming models allows for that. The parallelism, whether it's data parallel or functional parallelism, can be regular or irregular. With functional parallelism, it's more likely that it's irregular than not. But with data parallelism, this is indeed a major difference. So with regular parallelism, the tasks are similar, and they have predictable dependencies. So an example here is dense matrix multiplication. So a dense matrix is a matrix where all the elements, or almost all at least, are filled with non-zero values. So with dense matrix multiplication, one way of dividing the work is to say that you have one task that calculates each element of the output vector. So this is not really matrix multiplication, it's a matrix vector multiplication. So you have the matrix A times the vector B, it produces a vector Y. So in this case, we take the task of one element of vector Y is to take the row of the matrix and the whole vector B, and then you element-wise multiply the elements and then sum it all up to produce the Y value here. So, and then any kind of element here has the same behavior. You take the row and you take the vector B, and then you sum them up and produce an element in vector Y. So the tasks are similar, they're even equal in this case. They have predictable dependencies, exactly the same thing. This is in contrast then to irregular parallelism, which means that you have dissimilar tasks or unpredictable dependencies. We can again look at matrix vector multiplication, but in this case we are looking at sparse matrices. In a sparse matrix, a dominant number of the elements are zeros. So all here are zeros. And if you have a large matrix with most of the elements zeros, it's typically not very good use of resources to store all these zeros in memory. Instead, you only store the ones which are non-zero, the elements with dots here. And same goes for the vector. And same then when you do the multiplication, you need to you only do the multiplication where the elements are non-zero. Both of the elements actually are non-zero. And this leads to, in this case particularly, irregular data dependencies, because different tasks have different data to work on, and also in particular it leads to load imbalance, because some tasks may have no work to do at all, while some tasks, if defined as before, have a lot of work. And this is irregular parallelism, much more difficult to deal with. In particular, it will most often require some kind of dynamic load balancing to work well. Now, time for a quiz.